Hi there. Today we are going to look at a paper called as Perceiver, a general architecture for structured inputs and outputs by DeepMind. This has been recently in the news as a generalizable architecture that solves the time and space complexity of transformers. So by it can take any of the inputs from the images or text or any other formats and provide a generalizable output for that. There was a recently another paper called as Perceiver, which provides us an idea of this architecture previously. Perceive IO extends the same architect idea to the decoder values, where now the input can also be taken as any form of text, any form of inputs can be taken as an encoder. Same can be done for the decoder also, where any format of we can actually provide any format of the output that we wanted from the encoder. Now let's go on to paper. The recently proposed perceiver model obtains good results on several domains: images, audio, multimodal, point clouds, while scaling linearly in compute and memory with input size. While perceiver supports many kind of inputs, it can only produce very simple outputs such as class scores. Perceive IO overcomes this limitation without sacrificing the original appealing properties by learning to flexibly query the models, leading space to produce outputs of arbitrary size and semantics. So, as we mentioned, the Perceiver original Perceiver paper were were to provide a simple output as a classification or a regression output to the Perceiver problem, where Perceiver IO takes a step ahead and it provides the output based on the decoding process of what it wants, what the user wants to get the output format from. Now, this is a unique but a simple paper which just applies the same logic of encoder to the decoder, and we shall see the idea, architecture, and some codes along with that. So let's go with it. The idea of original perceiver is that it provides a generalizable algorithm which utilizes transformer architecture, but it also solves space and time complexity of transformers which occurs due to attenuation mechanism. Here you can see a general perceiver architecture can provide simple binary outputs such as a dog image from ImageNet, a audio from AudioNet, and some point word cloud is out data and provide some output around that. Now, perceiver IO architecture takes a step ahead in which it could provide the output of the optical flow estimation, some patterns from the images like here, and some outputs of the video also. Let me show you outputs from the video. But here you can see like what would be the flow of the for the burst flow would can be easily predicted by our perceiver. uh, if there are some patterns in the images which uh, it can also provide from the same architecture, and same for the video also it can deconstruct and reconstruct the video based on the same architecture itself without changing anything. Understanding the issue, let's take an idea of the language translation task in the transformer. Now, in general transformer, it works best because It can take a large value of input sequences at one go, which is helpful when our algorithm needs to reference other words for the context. So, to achieve a deep understanding of the context, every word is mapped with every other word to actually get more understanding. In a general transformer, our first input data goes through a multi-head attention layer through a feed-forward layer like this thing, and there will be multiple feed-forward layers based on the words. And this multiple forwards layer will be going through a self dot product attention layer, and then it will be moving to the next model of the feed forward layer. Now in the attention layer, each of the elements in the input is associated with all the other words in the input. Like it didn't would be matching with all the words in the input, and all this all as you can see, here also all the words are be mapped to every other words. For language class, as we are seeing right now, if there are m words in an input sequence, then because of its self-attention, the space complexity becomes quadratic as all the input sequence are be mapped to every other input sequence in a matrix multiplication. The space complexity mul- would be around m into m, which is a quadratic complexity. Now let's see this logic of attention in detail. Inside the self attention, we feed the input data into the three layers, which is the query, key, and value pairs. Uh, Let me query, key, and value pairs. So we would be feeding input to three distinct fully connected layers to create a query, key, and value vectors. This query and keys goes through a dot product matrix multiplication to produce a score index. As you can see, this is a this will be multiplied and a score value should be created. The scores matrix determines how much focus should be done to put a word to put a words in other words, and then we add a softmax to get the highest probability values, and it helps our model to produce more confident on which words to attend to, and it gets multiplied to value vectors to get an output vector. Because of multiplication between query and key transformers, in general, instances shoot upwards as the space and complexity increases. For language tasks, it was fine as a maximum of input sequences would be batched around 1000 or so. However, when considering images, our input sequence would be all the pixels in the image. For a simple image of 256 into 256, which is 256 of width and 256 of height, our pixels would be around 65,536. And this 65,536 would be fed to transformer as an encoder block, which would which would be multiplied as 65536 is to square. And a matrix multiplication of 65,536 would be done for attention of only one layer, which would obviously take a lot of space for any modeling purposes, and which is infeasible to do so. For that, several approaches came to provide, and and just right now, a new solution has been provided called as VIT, where images have been broken down into batches and fed them. However, still, if you see, it doesn't solve the quadratic complexity. It is just an alternative where the images can be just separated out, and so that the complexity would be reduced in a bit. But eventually, the input there would be a self-attention block where space complexity would be m into m square. So, what's the solution the perceiver provides? Let's look into that. Now, perceiver architecture generally tries to reduce this space complexity to a limit such that it should not be quadratic. Should solve this issue, they have introduced a cross attention block where the input sequences of the images between input sequences and a multi-head attention between input sequences and multi-head attention. So, what is a cross attention? Simply, in attention, where we perform matrix multiplication between the queries and keys, where the input would be of size m into m. If the query is of size m and keys are also size m, then the complexity would be around m into m. But if you take, let's say, an example of language translation, where we're translating a language of the English sentences to French one. Now, this English, there are six words on the English sentence. We will be moving to the input encoding, and then all the encoded words will be moving to the decoded words, where the our keys and values will be coming from the input sequences, which is of length 6, and our queries are coming from the decoded words. Now, if you see, two words has been decoded, which has converted from English to French, and based on that, it will be provided to the queries of this multi-head attention. Now, based on the all of this logic, then our output sequences should be moving again to the decoded values, and then next value should be predicted around that. So if you see on this particular example, the input is of length 6 and the output which actually goes to the keys, and the length of the keys and values would be around length of 6, and our queries, for example, if the two words has been predicted, so our queries would size would be around 2. So when we are multiplying, now our if the size of a decoder, let's take S and N size, and our encoder, let's take size of M as we take. Now the complexity wouldn't be M into M in this case. It will be M into N, where N is less than M. And because of this logic, the complexity now has been changed from quadratic to multiplicative, where it wouldn't be increasing proportionally as we have seen on the previous chart. Now, logic of this cross attention has been applied in the input sequences of perceiver, where our as we have seen, we have created a latent array space which provides the query values, and its length is of n into d, where n is less than m. If the byte array, which for example, let's take an image, is of m into c. When, for example, here they have done it for ImageNet, where the input sequences of byte m into c has been moved to the cross attention module, where the latent space was the size of 512. The output sequences that it provided was also of the length 512. The output sequence that it has provided was also of length 512. Now, at first, our latent space would only take a few input sequences from all the input sequences. However, now in the next step, again, these input sequences will be moving to the next latent array. Now, because of that, all the knowledge of the images, some of the knowledge has been moved from this latent space to the next one. So now our query has been optimized for the image part. Now, when it multiplies with again the input sequences, again there will be some knowledge that it will be capturing from the images, and then it will be moving to the next part. As you can see, because of this recurring nature, we can see it is as a simple recurrent neural net where the weights are also being shared among transformer blocks. That's this is a basic main idea of the perceiver paper. Because of this scalability, they have provided that it can be applied to images, text, and also for videos and audios also, and also for word cloud. As now they have gotten the solution where they can bottleneck any of the input sequences through a latent space which they want to provide. Because of that, now they can add as much transformer blocks, attention blocks that they needed for their architecture. This is the whole idea of the perceiver paper. Now let's move to the perceiver IO paper. Now, based on the perceiver architecture shared by DeepMind previously, they have supercharged the algorithm where they have added the cross attention mechanism in the last layers of the decoder also. Now you can see in the encoder also there is a latent space and the input query that has been provided to the attention block. In addition to that, now there is an other type of latent space which you can say output query array, which has been added to the last block of the attention module also, the transform module you can say, and that provides as a query, and all the values of the transform block our algorithm has been provided as a key and value pairs. Because of that, the size of the output that we do want to see would be of the same size of the output query array that we will be providing. The queries may be hand designed, learn embeddings, or a simple function of the output. They attend to the latent to yield an output array of the desired shape. Both the encoder and decoder take in two input arrays. The first is used to input the module's key and value networks, and the second is used as an input to the module's query network. The module's output has the same index dimension. There is the same number of elements as the query input. This is what allows the encoder and the decoder module to produce same outputs of different sizes. To capture the structure of the output spaces, we must make sure the query contains the appropriate information. This means the information query of the byte should be reflect the downstream task and ideally captures any structure needed in the outputs. This may include the spatial position in an image or the position of an output word in the sequences. Now, as you can see, the Perseus paper provide the best, the state-of-the-art architectures on the challenging task of optical flow estimation or tracking the motion of the pixels of the images. The color of the pixels shows the direction and the speed of the motion estimated by Perceiver IO. Basically, Perceiver IO provides the same latent architecture that we have seen on Perceiver and add it to the decoder also. So it can provide the output in any sequential length as we want from the algorithm to provide so. Now let's look at some metrics. Now they have provided trained the glue benchmark on the BERT and the and simultaneously on the perceive IO models. For BERT, they have provided for this time the inputs are and our latent space is an M. for that they have mentioned, which they have actually increased in the paper only. But let's focus that only. So now in the bird, the inputs are of 512 spaces, and the depth they have taken is 12, which is because the 512, the it takes this is simple a self-attrition model, and the accuracy is coming around 81.1 the best. The perceiver IO takes the input as 512, and the latent space they have reduced to 256. And because of that the depth that they can take from this is quite increasing, and that's what they have provided, and the accuracy also increases because of that. Same they have provided on the basic program also. The idea is that because of the perceiver IO, the depth that they want from the architecture that can get, because the latent space is uh, that is been using on the cross attention makes the attention block to get the data, get only few data in terms of their inputs. Now let's go to they have also provided some collab notebooks and code, which we will also go into that. Uh, Before that, if you like this content and do you want, if you really want to appreciate this, you can share a like or comment in the video description, and you can share some suggestions or any other comments that do you feel we should any topic that we should cover on the next papers or videos. So DeepMap provides the code, some of the collab books in their GitHub repo, but sadly, it can't be directly checked on their GitHub repo. But I will be saying some of the links in the collab books, which you can check it out from the link in the description below. Now, let's see some of the examples. This is a one, the ImageNet classification, where based on the basic idea that they have taken is I from the code we can understand uh, the basically they are the most of the computation that they are doing is been done on the jacks, which actually does improve their quality, and I understand that based on a Google product, it they will be using jacks on that. And if in this code, if you see mostly based on the image, they can provide the classification that which is the type of the image that we are seeing. Now on the another one, the mass language modeling. Here also they have provided an example where based on the input sentence, for example, here the input sentence they have taken is that this is an incomplete sentence where some words are missing, where the missing was a mass, they have masked the sentence, and so in the model they have provided sentence as the this is an incomplete sentence where some words are, and the next word has been predicted, and it has been done based on based on the perceived IO architecture only. Now for video and coding also they have provided the idea where the videos such as this example. Start at the outer core. Let me read it up. Has been constructed based on the idea, and they have provided the values here. If you want to me to go to the in depth of the code, let me know, and we can together go to each level of code and can understand what is going on. If not, we there is a Jax tutorial coming up in the next series, which we will be understanding more on the Jax function that they are taken. Mostly Jax is a next is a supercharged version of NumPy, and wherever you use NumPy, you can use the Jax logic for that. But that's it. Most we can there will be multiple. There are many more supercharged things that Jax helps in computation in a high dimensional values, which we will be seeing in the next parts of couple of series of videos. Now, finally, the optical flow, which the perceiver were talking about most of the time. Uh, Based on the images, they can provide the flow of the image, which they have provided the code also. Uh, I would say just check the code. So finally, we can see the optical flow, which the paper was mentioning about. You can check the code, and if needed, then and here's a code for the optical flow that they have mentioned. If needed, you can check the code in the link in the description below.
Here you can see the algorithm where it has deconstructed the video also based on the same architecture that has been provided in for the images and text also. And that's it for Perceive IO. If you like this content, then you can share a like on the video and do comment on the video and see you in the next video. Thanks.